In this video, I'm going to solve this continuity problem. So I'm asked to find a and b that make the following piecewise function continuous everywhere. So the first thing I do is I note what's happening on the intervals given here. So when x is less than 2, this function will be continuous because it's a rational function, and rational functions are continuous on their domain. So as long as x is not equal to 2, it is continuous. And this is how it's defined for x less than 2, so we're fine. These are polynomials, no matter what a and b are. So we know that these are actually continuous everywhere. So we can also say that the function will be continuous on the interval 2 to 3 and on the interval 3 to infinity. Problems could occur, though, at x equals 2 because the function is defined differently on either side of 2, and we could have a problem at 3. So those are the breakpoints that we need to be concerned with. So let's first make a note about continuity on the main intervals. So I've gone ahead and written that out. So since this is a rational function and rational functions are continuous on their domain, f is continuous on minus infinity to 2, and polynomial functions, which these are continuous everywhere. So we know f is continuous on this interval, but possibly not 2, and it's continuous on 3 to infinity. Where we could have problems, though, are at these breakpoints, x equals 2 and x equals 3. So those are the points that we need to be concerned with. So I'm going to start by considering the point x equals 2. And recall that if I want f to be continuous at x equals 2, what I need is that the limit as x tends to 2 is equal to the function value at 2. So what that means is that the limit, first of all, has to exist. So I need that the right and left-hand limits at 2 are equal and that they equal the function value. Let's first check the function value. So f of 2 is equal to, so for that I'm going to use this part of the function. F of 2 is equal to a times 4 minus b times 2 plus 3, which is 4a minus 2b plus 3. And that will also be equal to the limit as x tends to 2 from the right, because for that, I'm looking for the part of the function where x is larger than 2 and as close to 2 as possible, so I'm picking that. So that's going to be, again, I'm going to use ax squared minus bx plus 3, and I would get the same thing as above. So that's 4a minus 2b plus 3. Now, when I'm considering the limit as x tends to 2 from the left, I need to use this part of the function because as x tends to 2 from the left, we're thinking about what happens to the function as x gets close to 2, but x is less than 2. So for the limit as x tends to 2 from the left, I'm using this part of the function, x squared minus 4 over x minus 2. And that, if I evaluate, I get type 0 over 0, which is an indeterminate form. So I'm going to factor the numerator. Those common factors cancel, and I get 4. So what I know is that these things have to be equal if I want the limit to exist. So these must be equal. So what that tells me is that I need 4a minus 2b plus 3 to equal 4. Or I could rewrite that. 4a minus 2b is equal to 1. So that is one equation that I get. All right, so next I need to consider that other breakpoint, which was x equals 3. All right, so let's first consider f of 3. F of 3 is equal to 2 times 3 minus a plus b, because I need to use that part of the function where x is equal to 3. So I'm going to use that piece. And also I'm going to use the same piece when I look at the limit as x tends to 3 from the right. So the limit as x tends to 3 from the right is also, I'm going to use that same part of the function, 2x minus a plus b, and I get 6 minus a plus b. Now if I consider the limit as x tends to 3 from the left, I'm going to use this part of the function, ax squared minus bx plus 3, because I'm looking at values that are less than 3, but as close to 3 as possible. And so when I evaluate that limit, I get 9a minus 3b plus 3. And now what I know, if I want the limit to exist, so again, recall if the limit will exist if and only if these two limits, the right and left-hand limits, are equal, right? That'll tell me that the limit exists, and it will be continuous if those common values equal the function value at the point. So I need for these to be equal. So I need these to be equal. So now that gives me another equation. So that's going to give me the following equation. 6 minus a plus b is 9a minus 3b plus 3. And I can make that a little nicer, and I will get 10a minus 4b equals 3. So that's a second equation that must be satisfied for this function to be continuous. So I now have two equations in two unknowns. And so the next thing I need to do is solve that system. So again, we have two equations and two unknowns, and we need to solve this for a and b. So there are a couple of ways you can do that. The most natural way sometimes feels like back substitution, which is not that bad when you just have two variables. So I'll do that, and then I'll show you the other way, which is a bit faster. So to use substitution, you solve for one of the variables in one of the equations. So you start by doing that. So I have 4a minus 2b is equal to 1. Okay, so that tells me that minus 2b is 1 minus 4a. And if I solve for b, I get b is minus 1/2 plus 2a. Okay, and now I can plug that into the second equation. So that's the second equation. Okay. And so I get 10a minus 4 times minus 1/2 plus 2a is 3. So I have 10a plus 2 minus 8a is 3, which tells me that 2a is equal to 1. And so a is 1/2. So I've got a as a half. Now how do I get b? Well, remember, b is minus 1/2 plus 2a. So I can get b fairly easily now. So b is minus 1/2 plus 2 times 1/2 which is minus 1/2 plus 1, so b is equal to 1/2. So then my answer, my solution to this entire problem is the values of a and b that will make f continuous everywhere are a is 1/2 and b is 1/2. Now, I mentioned that there's an alternative way to solve this, which is perhaps faster. And the way I just did it is perfectly fine. But I'm also going to show you that alternative method. So let's talk about an alternative way to solve this system. So we notice that if I were to multiply this equation through by 2, I would get, or minus 2, I would get 4b here. And then if I added the two equations, it would cancel the b. So you may remember this method from high school. So what I'm going to do is I'm going to multiply the top equation by minus 2. And then solving this system for a and b is the same as solving this system for a and b. So minus 8a plus 4b is minus 2. And 10a minus 4b is 3. And then I can add the two equations. And minus 8a plus 10a is 2a. And as I said, 4b minus 4b is 0, so I got rid of the b. Minus 2 plus 3 is 1. And so now I have the equation 2a is 1, so a is 1/2, as we got earlier. Now, how do you get b? Well, you plug this in to your second equation. So you get 10a minus 4b is 3. So 5 minus 4b is 3. So minus 4b is 3 minus 5, which is minus 2. And so b is minus 2 over minus 4, which is 1/2. So of course we get the same answer, just solving it a different way.